Uh, Good afternoon, everyone. Uh, Looks we have majority staying online now. I hope we could have more people joining, but probably because of the weather, so many people stay online. It's our great pleasure to invite to have indeed have our last department seminar. You know that every month we have a department seminar, so this is our last one for this whole year. So it's our greatest pleasure to have our visitors from ARA, the Applied Research Associates from this ARA. It's a big group. They have different offices across the country, and it's our great pleasure to have Ms. Dale Meshter and Dr. Louis Rogowski from this ARA. And also we have Mr. Andrew Capodici from NEA, is the director of robotics. They are going to give us a presentation about the driver assistance and autonomy for operational enhancement. We appreciate your time. Thank you for our three speakers.
Hello, everyone. My name is Dr. Louis William Rogowski. I'll be presenting on the ADAS portion of this presentation and also giving a brief overview of ARA. And then Andrew will go off on the NEA systems and all the cool autonomous research that they're doing. So just a quick little introduction about ARA. ARA was founded in 1979 in Albuquerque, New Mexico, by a couple of people who just wanted to do really cool engineering stuff. Since then, over the last few decades, it has grown considerably into a nationwide defense contractor that has multiple different research and development interests, including working on infrastructure in the United States, ground robotics, healthcare solutions, and a handful of other things that I'm not presently aware of. Over the last decades, we have grown to 1,700 employees, and our company is 100% employee owned. So every one of us is a, owner of the company and helps direct it where it goes. And because of all the diverse research and development interests and contracting we've done, we were able to achieve a revenue of $486 million in FY22. So that is a 15% revenue growth from last year, and we grew 10% in employees last year as well. So this is just a brief company profile of everything that we do. In terms of our breakdown, engineers and scientists make up the vast majority of our staff. So roughly 69% of us are have some kind of technical background with professional services, technician, administrative staff, management, and interns, also leading the backbone of our organization. So at this time, I'd like to mention that if anyone is interested in interning at ARA, we are always encouraging it and could honestly use the help for all of our projects. Just another quick breakdown of what we are. So 45% of us typically have a bachelor's degree, and then about 49% of us have a master's and PhD. So you'll notice that this doesn't quite add up to 100%. So some people have associate's degrees that weren't listed there. And also 15% of our staff are military backgrounds. So we appreciate their support to ARA. So these are just some of the business areas that we typically work in. National security is a big one. We typically build these little sensors that we can put in the ground called Pathfinder receivers that basically, if people walk near it, it can detect footsteps within 25 meters. We typically deploy these around military bases and other critical infrastructure. We also develop Sentinel security systems that basically act as like little mobile command centers where we can detect threats in real time, and we have those typically deployed around Air Force bases. We also develop a variety of different technology like non-visual weapon detection and like counter UAS technology. In terms of infrastructure, we help develop some of the security systems that protect our nation's capital. Like if you think of those road pylons in DC to prevent cars from going through it, we've had some input into those designs. We also develop paving systems that can perform accelerated load testing on a variety of different road formulations and things like that to collect data. In terms of energy and environment, ARA has developed alternative fuel sources, mostly in forms of renewable biodiesel. So using a patented process, we're building plants across the US to produce that process. And then also in terms of health solutions, we've also made great strides. Using machine learning technology, we've developed sensors that can be wearable on Army personnel to detect sepsis and also detect if they're about to go into shock. We also work on microrobotics technology, where minimally invasive robots can go inside the body and perform targeted drug delivery. So just to give you a little bit of an overview about our division, there's actually two divisions here. One is Integrated Products Division, the other is NIA Systems. NIA will talk about everything that they do at the end of this presentation, but for now we'll focus on integrated products. So our base is located in Randolph, Vermont. We have a 63,000 square foot facility where we do a variety of different things, including fabrication, electronics, machine shops, and dedicated research and development labs. We're a ISO 9001 certified facility, so quality is ARA and ARA is quality. We have a 47-acre test site to test anything that we make. And we also have government-approved inventory control. So we have a lot of things going for us. We just opened up a new office here in Greenville, South Carolina in August, where they're supporting and performing, like systems engineering, mechanical, electrical, and software engineering. This is also, if anyone here at Clemson is interested, this is probably a good place to intern at. So second plug for interns today. Our capabilities, again, include systems engineering, research and development, mechanical, electrical, software. We have technicians, we're Six Sigma certified, and we perform production and product engineering. So just to give you a quick overview of the IPD's focus, we primarily work on robotics. In this case, what we'll show in this presentation is our third generation Autonomous system. These are basically modular kits that can be applied to commercial and military vehicles to turn them into fully remote controlled devices. So you can either control them with a handheld remote, or you can do teleop, where you can look through a tablet and receive camera streams and control them using like an Xbox controller. And you'll see a lot more demos of that today. We also do geotechnical work. So we develop cone penetrometer testing systems to actually collect soil information and collect data that might be relevant to construction sites. And again, we also build that pavement testing machine I talked about before. And like I already mentioned, the the Pathfinder system, and we also develop ecosystems that can be attached to machinery to collect data about that. So we do a lot of cool stuff here. I enjoy working here. This is everyone else here. So a lot of neat stuff. So today we'll talk about robotics, and then we'll jump into some of our ADAS features. So this is just a brief history of all of the ARA robotics that we performed. It starts here in 1995, but we have roughly 40 years of experience in this. So one of the first projects we did was the ARTS project, where we outfitted these with MRAC kits. So MRAC is the precursor to the Autonomous system that I mentioned before. I believe these were developed to help with airfield repair. So if an airfield got bombed, you could actually just send out these robots under remote control to remove unexploded ordnances and repair the field without causing, injury to human life. We've also worked on drones over the years, such as the Nighthawk and the K-Hawk. We've integrated these robotic systems into skid steer-like devices, and also, foresting equipment and things like that. And more recently, we've started equipping these devices to things like the Polaris M-Razor, the M-Razor Alpha, minefield robots, and of course, Humvees that are being upgraded retroactively. So this is kind of an example of the architecture that we use. This is an integrated platform with our Autonomous system. So probably the brains behind everything is actually this little VIC controller. It's called Vehicle Interface Controller. So basically, this provides all of the robotic controls. So this will be plugged into all of the actuators on the system, like steering actuator, throttle actuator, and monitor like everything that's going on inside the vehicle. We use an IOP and raw-based front end and with a redundant CAN back end. We also use a safety processor to make sure we don't accidentally kill anybody. And we also talk directly to M-Razor systems. So the second thing on here is the teleop kit. So this teleop kit basically performs a lot of machine learning and also connects to our radio interfaces, camera interfaces, and IOP interfaces. So if you think of this vehicle, let's just say this is a M-Razor right here, and it's far off in the distance. We can connect to it using a mesh network of radios, and then using those radios, we can use these operation control units, like either a handheld USB remote right here, where you can control driving direction, acceleration, etc. Or you can also use one of these tablets in conjunction with it to see where the vehicle's going, etc. And I believe these radios go out to about 2 kilometers with line of sight, maybe a little bit more. I'm going to let NEA talk about their autonomy kit and all the cool stuff that they do, but basically they can do waypoint navigation, object detection and avoidance, GPS navigation, GPS denied navigation, and follow me, where the vehicle basically just tracks you as you walk along. So this is where the meat of the talk is, and this is probably where more of the technical data comes from. This is our advanced driver system, or advanced driver assist systems, also known as ADAS. These can be integrated into vehicles that have the Autonomous system or standalone. We've actually integrated this system into a vehicle recently that was tested at AM General Proving Grounds out in South Bend, Indiana. So this is just a brief overview of the system that we have here. So a lot of this is the vehicle interface and throttle shifting actuators, ARA brake, etc. But we also have a lot more sensors on this now to integrate into all of these ADAS features. So we have a stereo camera at the front of the vehicle, a long-range radar at the front of the vehicle, an IR camera, and an EO camera. On the sides of the vehicle, we have two short-range radars, and at the back of the vehicle, we have a backup EO camera and a short-range radar. There's a bunch of other goodies on here that's not particularly mentioned, mostly side cameras, but we're not going to really see a demonstration of that today. So this little interface right here is actually what would be mounted inside of a vehicle just arbitrarily. So we have all of the different ADAS features at top that can be toggled on inside the vehicle. These can also be toggled on if you're inside that little tablet interface that I showed before. So all of the current ADAS features, and a lot of these we're going to show today, include blind spot monitoring, forward collision, adaptive cruise, and lane departure. The two I'm not going to show are park assist and rain sensor. So park assist is basically, there's just a short range radar in the back, and if an object gets within like 1 meter of the rear, the vehicle just stops while it's going in reverse. And the rain sensor just detects if it's raining outside. I know that seems obvious to the driver, like you'd know if it's raining outside, but it actually allows us to trigger turning off certain ADAS features for safety reasons, like adaptive cruise control, for instance. So I just want to provide a quick overview of blind spot monitoring and kind of what it looks like when we look through a tablet and things like that. So this is that Zebra tablet that I showed before. So right now we have a vehicle that's equipped with this whole Autonomous system, and I'm basically just changing different views. So I looked at forward camera, rear camera, infrared camera. I forgot to mention that there is an IR camera on here. And I believe this last video is the lane detector. So we actually developed an interface where you could actually see like lanes moving around. So these cyan lines represent actual road lanes. This is getting some fake detections there, but this magenta line also represents a complex lane detector, and I'll talk more about that. And it's more for like Jeep trails and things like that. So just to quickly demonstrate blind spot monitoring, I had a colleague of mine, Jeremy Kolb, walk around the vehicle while I was recording this video. So you'll notice right away that let's see if I can get my mouse over there. So their right is flashing already. That's just because there happened to be a vehicle parked too close by. So it was just triggering in this particular instance. But you'll see that the left will trigger and then the rear will trigger as he walks around. So he started on the left and then he goes to the bottom. So we also have a forward blind spot detector. In this case, it's called pedestrian detector. So this is a little bit more complicated. So where blind spot monitoring is just rear and side radar is triggering if something's there. Pedestrian detector actually looks if there's a physical human being in front of this. So using that forward EO camera, we take all the image processing data from that, feed it into a machine learning algorithm, and it tries to determine if a person is there. And then we also have the same thing with vehicle detection. So I'll play this video. Sorry about that. Yeah, so you can see it was going off with him walking around. Play that one more time. Yeah, so it's going off, and then he's just walking around and says hello. Okay, so probably a more complicated ADAS feature that we'll start with, and then we'll get into a little bit more complicated stuff, is forward collision detection. So this is actually a fusion of different sensor data that's being input. So we're still doing that machine learning process where we're looking for either people or vehicles in front, but now we're also combining that information with forward long-range radar data and stereo point cloud data. So essentially how this works is that if a person is detected just anywhere in this field of view, a radar point is the closest radar point that's being detected, closest to the vehicle, is going to be assumed to be that person or vehicle. Now, you can make this more precise and say, hey, why don't we just pick a radar point that matches where the location of that person is? And that's fine. We're going to do that. It's just when you deal with point clouds, as I'm sure a lot of you know, there's a lot of computational processing going on. And we found it was a little hard to get that to a point where it was actually safe to operate. So basically, we just pick a radar point that's closest to the vehicle, and we start tracking it using a basic Kalman filter. And then that data is fed to a different control system, which basically applies brakes proportional to the distance of that person or vehicle away from the forward of our vehicle. So, and I'll talk a little bit more about the PID on the next slide. So this video is just a quick demonstration of a pedestrian being tracked by a collision detector with position and distance estimates represented on the top left here. So these are simulated road lanes that are just like arbitrarily placed in front of the vehicle. So only radar tracks inside of this are actually going to be considered valid targets. And then again, these little purple dots are radar detections. So this was an intern, Jack, who was kind enough to volunteer for this. And you can see the green circle represents its estimate of where he is. And then he walks out of the field of view. One thing I want to point out that I forgot is at the start, this cyan dot in the middle, this is actually estimating where it thinks a vehicle is. And there's a lot of vehicles in this field of view. We have a track rig over here. There's an M-Razor over here. So machine learning thinks there's something there. So that's all well and good. That was a standing demo with no one in front of it. So I wanted to give you guys a demonstration of forward collision with an actual target in front of us. As much as I'd like to use interns, management has refused to let me do this with a moving vehicle. So instead, we have to use Major Payne over here, who is our dedicated cardboard cutout. So, and he's not afraid to, he doesn't try to jump away from the vehicle. So again, same thing. In this little demonstration video right here, you see me walk out there, and the collision detector is actually tracking me pretty nicely. I'm trying to fix Major Payne because I wasn't getting, the machine learning wasn't registering him correctly. So I'm trying to stand him up a little bit straighter. And I walk back. So essentially what's going to happen is I'll back up the vehicle and then drive forward. And I want to point out it's actually not tracking anything in a second. So it doesn't see anything in front of it. And then as we get close enough, the machine learning algorithm picks it up, and then the vehicle grinds to a halt as brakes are being applied with the PID controller. One thing we found is we actually had to tune the PID controller a little bit more to actually apply the brakes, because sometimes it wasn't applying them fast enough. And sometimes we'd collide with the target. So good thing is made out of cardboard. This is a forward collision detection with a vehicle demonstration. So the same guy, Jeremy Cole, was parked in his vehicle up front. He was kind enough to volunteer it. And we just performed the same experiment. So we see all the radar tracks. We're not tracking anything at the moment. We don't see a vehicle. And as we move forward, as we get closer and closer, we see a vehicle, and then the car drives to a halt. So when we look at this graphically on this first figure, technical difficulties. So as we look at this first figure, I'm just manually applying the brake right about here. And then I let it go, and the vehicle starts coasting towards his car, maybe at like 2 or 3 miles an hour. And then when it actually detects it, we see that brake starts applying proportionally. And just to explain what this graph actually represents, we have an effort percent here. So when we're dealing with brakes and throttles, we just measure a percentage of how far it's depressed on the vehicle. So 100% means the brake is fully to the floor, and 100% throttle means we're going as fast as we're allowing the vehicle to go. I think in this case, we can go a maximum of like 9 meters per second. So don't be alarmed by efforts greater than 100%. This is actually we have back-end algorithms that just set this to 100% if there's anything over it. So that's just the PID loop being weird. We also measure in the secondary graph here the distance to the target. So all of the zeros at first is just we're not seeing anything in front of us. And then eventually we do see something that's about roughly 10 meters away, so 30 feet. And then we grind to a halt at around, I forget what the video said, I think it was like 7.6 meters away. So building off of a collision detector, now we can talk about adaptive cruise control, where we're actually trying to, instead of avoiding colliding something, we're actually trying to follow the vehicle in front of us. So adaptive cruise will do one of two things. It will maintain a set speed of the vehicle. So if I'm in this little, vehicle behind the leader vehicle and I don't see the vehicle, I'm going to go whatever my set speed is, 5, 10 miles per hour, whatever. But as soon as we see the vehicle in front of us, we're going to start trying to maintain a follow distance behind it. So in this case, we use a PIDQ controller to adjust the vehicle set speed to try and maintain whatever set distance is, whether it's 5 meters, 10 meters, or 15 meters, et cetera. So in this little simulation graph on the left or on the right over here, what we're doing is we're having a leader vehicle move at 1 meter per second, and then it accelerates to 5 meters per second. So looking at so you can see that in this controller output velocity. In the second graph, we're trying to estimate the position of our vehicle versus the vehicle we're following. So apologize, there's some lag on the mouse. So if our vehicle is trying to follow this vehicle, this axis is the x-axis. And we can see that, given the positions of the two, we're actually, tracking it quite nicely. And when we actually measure the following distance with time, if we're trying to maintain a 10-meter following distance, we're about like 1% error. So actually pretty good. So when we actually do a demo of this via adaptive cruise, where we're actually trying to follow a leader vehicle, I'll walk through this as much as I can. But I also have two graphs on the side that basically show how brake and throttle efforts and distance measurement change with time. I think at first we were trying to just 10-meter set point, and then we changed that to a 15-meter set point. So we'll see. So he backs up at first, and my foot's still on the brake. So probably right about here on this graph is where we start moving. So as we start moving, my vehicle's moving at a crawl, basically. And then when he gets far enough away, my vehicle will start to accelerate again to about whatever the set speed was. I think it was like 4 miles per hour. So you can see we're moving along, and then he actually brakes his vehicle. And then as I get closer, we start tracking the vehicle, and eventually the brakes get applied and our set speed changes. So, and you can actually see it here. We accelerated and then we slowed down, and now we're accelerating again, trying to catch up to him. And I think as soon as I come around this curb, we are actually just going to stop, if I remember right. Yeah. So I'm very sorry I can't actually show you my vehicle in these videos. There were some restrictions we had to deal with from the government. But basically in the secondary graph, you can see all the distance with time and how sometimes we lose tracking, and that's fine as long as we pick it up again within a reasonable time and don't collide. It's more than fine. All right, so the last part of the ADAS features that I'll talk about today is lane departure systems. So in our vehicle, we actually have two lane departure systems that are working in parallel with each other. So the first one is road lane departure, and the second one is complex lane departure. So road lane departure is exactly what it sounds like. We're looking for pristine road lanes, and we have a machine learning algorithm that can actually, extract these road lanes from whatever the forward EO camera is doing. And then using a combination of image processing and linear regressions and other logic in the background, we can try and estimate when this lane is departing versus when we're safely inside the lane. An idea was posed while we were doing this project to do complex lane departure, which is achieved using a separate neural network. And the idea behind this is if we're having vehicles move around in like complex environments like Jeep trails and things like that, we need a way to, try and develop a lane from that. So we had a lot of footage that was collected by ARA staff, but we also developed these simulated data sets where we have these, where we used a Unreal Engine to actually produce like these fake dusty environments. So like this is just a trail, and then there's dust clouds coming over. We also did this for sun glare. And then in the annotated environment, you can see we kind of identify what the smooth trail looks like, what rough trail is, foliage, et cetera. So when we apply this to a simulated model, we can see that this real live Jeep trail right here, we can see that it's actually classifying this pretty nicely. So how about we see some demos of this actually working? So the left will show complex lane detection, where the magenta line represents an estimated complex lane, while these little white lines here represent estimated intersections of where it thinks it is. And you can see the algorithm actually works pretty nicely. It's detecting the Jeep trail. All right. I apologize if this is all pixelated, but seems to be a common effect with Zoom. And you can see when we hit the intersection, it's trying to give the driver a prediction of which way it could potentially go. So unfortunately, I don't have a video showing both of them working together. This video kind of shows it on the right, but this is more showing road lane departure. So as we start departing the right lane, when this turns yellow, it'll actually send an alert to that ADAS tablet I showed you before, and alert the driver that, hey, we're going out of lane. You should probably adjust. And you can see complex lane detector trying to do stuff. And it does work in certain urban environments, but because it's wintertime and there's not really a defined trail in front of us, it's just seeing everything around it. So this will turn around and eventually do another departure. I think I do right lane again. Yep. Let's see it go. I'll let this play to the end because I think it does try to map out this little trail at the end here. Yeah, it does a little bit. And you can see we get kind of a false detection there, but you can see it actually does outline this trail fairly nicely. Again, snow and stuff wasn't designed for it, so odd things happen. So just some closing thoughts on ADAS and all of our systems. I wish I could have showed you a lot more videos, but you saw the important ones that I felt were good to see. So as we saw that, ADAS can greatly improve the ability of drivers and can prepare them for diverse situations. We saw collision detector work fine, and collision detector will work up to like 20 miles an hour from what I get, or up, let's say up to 10 actually, maybe up to 20. But then we also saw adaptive cruise control, and then lane departure, and also blind spot detections. And we can integrate these features into autonomy and potentially remote in the future. We're already doing it with drive-by-wire, where we have the tablet, we can actually see a lot of this stuff trigger and happen, but we can make this way more complicated. And as we saw, integrating these ADAS features requires multiple subcomponents and a great deal of time and testing. So that wraps it up from my end. So I will pass it over to Andrew, who will do the NEA systems overview. Thank you.
Sir? Does this work? All right, good afternoon, everyone. My name is Andrew Capodieci. I am the Director of Robotics at NEA Systems, and as was mentioned earlier, NEA is the Advanced Autonomy Division of ARA. So let me see if I can get this quicker to work. All right, and I'm going to talk you through some of the work that we do in off-road autonomy, which is our focus. And so as I've mentioned, NEA really focuses on the hardest challenges in off-road autonomy. So the types of environments that we work on are driving through a forest. You've got tall vegetation, a few meters high. You are trying to perceive through multimodal sensing, be it LiDAR, camera, radar, etc., that the vegetation is traversable. You are trying to still detect the boulder that's hidden underneath the vegetation, and then also see that there's a cliff that you're about to drive on, and still try and find your way through these environments that you've never seen before. And we do this on a wide heterogeneous set of vehicles. You can see a variety of vehicles we've integrated with since roughly 2009, when NEA was founded and we were acquired by ARA in 2017. Our focus is primarily on the ground vehicle side, where we've worked on anything from a small EOD robot you can pick up with your hands to a side-by-side John Deere style vehicle, all the way up to multi-ton construction and mining vehicles. And we also do some collaboration work where there's a team of a ground vehicle and a drone that are performing some autonomous mission together. Now, NEA's capabilities are focused again in this off-road space by performing first autonomy and navigation. So given a vehicle and a kinodynamic model of that vehicle, we are trying to figure out what plan to take through the environment. That's the navigation piece. We fuse all of that multimodal sensing that I referenced, which is the next perception AI machine learning. Again, we work with every sensing modality, including the LiDAR, the camera, thermal, radar, etc. We also work in multi-robot mission planning, which I also referenced in terms of a fleet of vehicles that is more so than just a single paired drone and ground vehicle, but you could have a whole fleet of ground vehicles performing some coordinated behavior. The example I like to give here is you could send 2 drones out to survey an area. If they detect an object of interest, they forward that position over to the ground vehicle. The ground vehicle is given that location and drives out to intercept. And then you can have a smartwatch or a phone of some sort that the operator is leveraging to receive that data and then task the vehicles in terms of what should happen next in the mission. Simulation, as is useful for anyone developing autonomy, robotics, and engineering in general, is a key part of our stack, especially because we've got so many complex pieces to these robotics vehicles, all the way from the platforms themselves, the electrical, the mechanical, all the way up to the core software, which is the heart of the autonomy. And then, of course, standards and open architecture, especially when we get into the mission planning pieces, is especially relevant given we've worked on so many heterogeneous vehicle sets. We need to make sure that we can command and control these vehicles using a common framework. Specifically in the perception realm, which in my opinion is the heart of autonomy, and I think many people would agree with me, I often reference 5 fundamental failure modes in off-road autonomy, and you can see them listed here. They are negative obstacles, which is trying to perceive a cliff, a ravine, or a void in your signature response. You've got thin obstacles, a good example being concertina wire or chain link fences, where especially at range, the signature response is either non-existent or extremely small. You've got the other side of that coin, which is vegetation filtering, where you have these what can be relatively small obstacles in terms of the stems and leaves of vegetation that you are detecting, but trying to register that you can actually traverse through. You've got inclement weather, which is very much shared with the on-road space in the form of rain, snow, and dust. And then on the bottom left there, you've got water detection, which can present itself in many forms depending on the particulate density of the water, the depth of the water, et cetera. So a lot of these things, I would say the first 4, negatives, thins, vegetation, and water, are things that on-road does not have to deal with as frequently. Inclement weather, I think, is shared. And these are the types of problems that we try to tackle in these rugged off-road environments. I've got a video here showing our stack, so let's see if I can get this to play. And what you'll see here is our main IRAD test platform. It is based on an M-Razor X diesel electric hybrid. You're going to see 2 behaviors here running on our 80-acre off-road test site. The first behavior here is waypoint follow. So we've got relatively coarse breadcrumbs that are defining a path up to the forest. Using our mission planning layers right at the forest, we've drawn a phase line, and the vehicle will automatically transition from the waypoint follow in the open area where you've got GPS accessibility to a go-to-point behavior. And it has no a priori data. When it enters the forest, it is seeing this environment for the first time, and using a combination of LiDAR and camera, it is building up a map of the environment. It's localizing in a GPS intermittent scenario, and so there will be stretches inside the forest where it's completely GPS denied. It is localizing where it is, aggregating the perception data to build a model, and given a single point that it is trying to achieve at this point in the video, it's somewhere over to the right. It is trying to figure out what path it can take through this environment to achieve that goal point. So right here, we've passed that phase line. The video is coming through a little choppy, but this vehicle is fully autonomous. We've got a safety driver in the passenger seat, again, just for safety purposes. And as I mentioned earlier, there is a point off to the right. So the vehicle right now is seeing this environment for the first time and trying to figure out how can I exit and start to enter into the congested area of the forest to achieve this goal. You'll see that it is following the trail right now, not because it has a model of the trail or because it's detecting the trail, but purely because that's the open region of space in this environment. And ultimately, it will find a path over to the right in a second here, where it can fit through, and we'll start to navigate towards that single point that it's been requested to achieve over within the trees. One of the core differences between what we do off-road and on-road is the depth to which we have to perform ground surface estimation. And again, we have no a priori data. We don't have a road network. We don't have a dense map against which we're localizing. And so we have to figure out what portions of the terrain can we even drive on. And so to that effect, we just drove under a rope. And so we're modeling that ground surface. We've got a model of the vehicle. and we know that the vehicle can fit underneath that rope. And then here, as we enter a particularly congested area, you can see the vehicle doing multi-point turns to fit through. This M-Razor vehicle has quite a large turning radius, so those multi-point turns definitely become necessary in these hyper-congested spaces. And ultimately, we'll achieve that point here. And again, this was a single point. We had no route data. We'd never seen this before, and we were perceiving it all on the fly through a combination of LiDAR and camera data. All right, jumping to the next slide. This is another behavior that we have that leverages a lot of AI/ML. And so person following is something that you'll see in these off-road cases that is particularly useful both in the commercial and the military use cases. And we have performed these person following behaviors with every type of sensing modality individually. So with just monocular vision, with just LiDAR, and with just stereo, and we've also fused them all together to improve the reliability. And we've done this on a number of vehicles here, but you can see in various environments where we've tested this. Again, this is leveraging a lot of ML here for the person detection, which is a very common application of ML. And then this target is fed to our autonomy and navigation stack, which I believe I should have a slide on, hopefully coming up. But I'll speak to it a little here just in case I don't. But the autonomy and navigation piece is essentially taking the target location here, building a map, and then identifying essentially what vehicle controls should we execute to make sure that we're following this person at a safe distance. Mission planning side is again leveraged to coordinate a team of both unmanned and manned assets. And so I think that manned portion is particularly relevant to make it clear that the soldier in the loop or the operator at a mining site can task and be part of the operation that you're trying to run. So I referenced earlier a case where you could send out 2 drones, fly over an area, and try to identify a target, have that relayed to a ground vehicle that would go to intercept. That's the type of mission set that you are coordinating with this mission planning layer that is enabling force multiplication. There are a suite of AI tools that automate the generation of the mission, the allocation of assets in an optimal way with respect to things like time to completion or resource consumption. And then there are also pieces that will automatically schedule different parts of the tasks based on dependencies that may be shared between them. And this has been actually the first program that NEA ever worked back in 2009 was a SBIR program in mission planning. And this work has continued to this day. Simulation, another one of our capability vectors, which we stood up for the off-road case. There's a lot of work on road, but as I've talked to a little bit in this presentation, the requirements for perception and planning off-road have a lot of differences. And so we have taken some open source tools like the Unreal Engine and Carla and built on top of those the off-road pieces that we're missing. And this originally was stood up out of our own necessity since, as I've mentioned, autonomy development requires simulation. It's extremely useful so that you can significantly reduce the use of on-vehicle testing, which is costly with respect to human resources and vehicle resources. And in the act of creating this ourselves after the Anvil simulation piece, which was primarily what was used off-road, got bought out by the on-road industry and disappeared for those of us in the off-road space, we generated this ourselves with some sister divisions in ARA, specifically Virtual Heroes Division, which specializes in simulation. And we built this out with things like vegetation-aware LiDAR, which are, again, enabling the off-road simulation pieces that we really need here. And it turned out that just like we need it, there are other developers in off-road space, and this has actually turned into a funding stream for us as well. So this is something that's being actively developed, has been useful to other parties. And the way that we use this is ultimately generating those thousands and thousands of test scenarios to accelerate our testing. And so you're able to drive perturbations of the scenario, evaluate metrics, and really hammer on capability again with that off-road focus, adding to the perceptions fidelity in these off-road environments. And here I've just got a couple of other programs that I want to speak to in terms of the type of off-road autonomy that we work. So I mentioned negative obstacles earlier. In the top left, this is a program that we're working now where we are pushing the state of the art in terms of what an off-road vehicle can do to detect things like cliffs, ravines, potholes, etc. We just, I believe 2 months ago it was, ran our first demonstration on vehicle where we had that same MRZR X platform that I showed driving in a field on one side of a ravine that was about 3 meters deep. We clicked a point on the other side of the ravine and ran the system just to make sure that the vehicle correctly detected that negative and did not try to drive through. This was through a fusion of both LiDAR and monocular imagery. So as we're driving through, we are processing that LiDAR data, analyzing things like the sensor field of view, the noise variance within the cost map, as well as rain shadows, and looking at ray tracing to see if voids in the terrain are a cause of obstruction from positive obstacles or could in fact be a negative obstacle. And then we've also got some image-based detectors that are looking at intensity gradients in sort of a sandwich form. If you think about the meat of the sandwich versus the bread, looking at intensity gradients going through those three areas and cross-correlating that with voids in the LiDAR data to ultimately detect these negatives. And we show that we were able to do so up to a range of about 40 meters. And so that vehicle would drive around left and right, trying to find a way past this long ravine, and ultimately decided that there was no path across. In the top right, we've got work that we are actively performing in vegetation perception. You can see an example here in the slide. On the left, there is a tree. And in terms of temporal and spatial consistency of these positive obstacles that are technically vegetation, being a tree, on things that you cannot drive through, there's a lot of temporal and spatial consistency. You can see that this graphic is visualizing the multi-return variance. There's also almost no multi-return variance on the ground and on true positive obstacles. But when we look at, on the right, the bush, as lasers slice on stems and leaves, you see a lot more variance. And if you played this as a video, you would see there's a lot of not only spatial variance here in this single frame, but also temporal variance from frame to frame. We're queuing off those to detect the traversability of vegetation in the scene and differentiate that from positive obstacles, which goes back to that first scenario I mentioned where we've got tall grass, we're trying to identify that we can drive through it, still see the boulder underneath, and detect that cliff on the other side. In the bottom left, I referenced some of our commercial work. This is in the mining space where we're fusing about 16 different sensors, stereo, LiDAR, radar. And this is showing dynamic tracks of obstacles across frames. The interesting thing to note here is that this is going to be one of the first safety certified perception stacks in the world, which will adhere to IEC 61508. We're also just kicking off an effort here to generate a military version of this stack, which, if I remember correctly, will be also safety certified against MIL 882E. And if anyone's worked perception, they know that safety certification of those pieces is extremely difficult. So that's going to be a huge win for us. Those programs are currently underway now. The commercial side has been underway for 1 to 2 years. The military side is just kicking off. And then finally, in the bottom right, we are working on a next-gen rugged navigation package for specifically off-road SLAM. So again, there's a lot of work on-road where you've got this dense 3D map that has been built up over time and is heavily maintained. In a lot of our environments, we're seeing them for the first time. So this is focused on SLAM that's closing the loop in completely novel environments. And that is it for my presentation here. So I think we can open it up to questions if anyone has some. Yes, sir. Yeah, it is proprietary. I mentioned we did build it on top of some open source tools, but then added proprietary layers for the off-road specific pieces like the vegetation aware LiDAR. That is something that we have developed contracts or essentially been awarded contracts to work with third parties. So that is an avenue, but it's not something that's open source. Yes, sir.
You're looking at fusing a number of these algorithms. You presented like a pedestrian detector. How much of this is developed in-house? How much of it is taking best in class? And if so, how much tuning is required? And finally, of course, I think there's an opportunity for metrics, quantitative, that go beyond just it looks good. If you could speak to that, that'd be good.
So yeah, so to answer your questions, so the original person that was working on this, all of the ADAS features, I believe he was looking at best in class and then tried to put his spin on it, and then I basically just ran with it. And a lot of this has been developed in house. And like we definitely read research papers and stuff about what other people were doing, but we kind of just try to do our own thing. Jumping forward ahead to metrics. So all of those systems were tested at the AM General Proving Grounds out in Indiana. A lot of it worked. A lot of it had opportunity for improvement, but we got a lot of good feedback from that we're actively working on. What was your middle question? Sorry.
I forget myself, but maybe to pull on that last thread.
Yeah.
I think I have to first congratulate you on making sure that an end-to-end system works and works with this capability, so that there's no second guessing that. But I'm curious, from a V&V perspective, is it something that you say it kind of sort of works? It works in most of the cases, or you now do some provably correct guarantees of like percentage completion, so on?
Oh, I see what you're saying. Yeah. So when we tested collision detector, for instance, we basically did that mannequin test like 5 times, basically, and it succeeded 5 times. And we did that at various speeds. We did that slow and then fast, etc. With the adaptive cruise control, where we were following that vehicle, we followed a vehicle at night, basically around our facility 5 times. And it only screwed up 1 time, if I remember correctly, towards the end. So 80%. There's definitely room for improvement there, for sure.
Yeah.
But
would you have an interest in sort of ways in which you could now get, let's say, more data without actually having to do the test physically?
So I can add, I think, some data on, you specifically asked about the person following side of the equation. Is that correct? Exactly. Right. So in the person following case, which was the slide I showed earlier, that's a case where we're not developing a new piece. We're taking advantage of what exists. So things like the 17 versions of YOLO that exist, some of the instance segmentation algorithms and things like that. So in terms of metrics, we selected best of breed in things like person detection, because that's been so heavily researched and things are so performant, it's not in need of novel behaviors. The cases where we are developing novel algorithms is more closely related to the 5 fundamental failure modes that I referenced. So the negative obstacles is a completely novel stack, and then the vegetation filtering. I did reference the singular metric that we're able to detect that ravine as far out as about 40 meters right now. That's primarily a result of the resolution of the LiDAR. So that's using an OS164, so a 64 scan Ouster LiDAR. And the limiting factor there is the, based on how we've mounted the LiDAR, which is pointed slightly down, because in a lot of off-road cases where we can't move as fast, and we need to perform the traversability estimation doing that ground surface modeling. So we want a higher density in that 0 to 40 meter range. And if you increase the resolution, or even if you change the orientation of the LiDAR, or some of the new LiDARs now have the ability to dynamically modify or control the scan pattern. So you can change the mean of that Gaussian distribution of scans. If you increase the density at a farther range, you could improve the maximal range of detection of negatives, for example. But this was our first experimentation on vehicle. So right now, that's as far out as essentially our LiDAR horizon supports, which is to say that at about 40 meters, the distance between scan lines becomes larger than the ravine itself. And at that point, our detection fails. And so for negatives in vegetation, we start off with that off-road simulation. We generate a set of progressively more difficult simulation scenarios. So the first one is going to be drive straight towards a cliff. And then we scale up from there. We approach it from every angle. We start to add positive obstacles. We perturb the environment in terms of vegetation, inclement weather, et cetera. We build up that simulation set, and I've got metrics for those. I don't have them readily available, and I can't show them yet because they're not approved for distribution, because that is a military contract. But what I can share is that sort of system level demonstration. We're able to see, and at a system level, not drive into the ravine, see it at 40 meters, and weave in and out to say, can we find an opening to progress through? And in this case, there was literally no way for the vehicle to get to the other side of the ravine. It was closed off. And so from a system level perspective, I can say that it worked well enough that the vehicle never decided to drive into the ravine over the course of about a half-hour test. And then if I get those approved for distribution, I can give you more details. Yes, sir.
Yeah, I guess you kind of answered this already, but since you're using like deep learning end-to-end approaches, what is the process for identifying like these boundary cases or unexpected use cases that the machine learning can't handle? So do you have a process, and what is that process?
Yeah, and it's especially more difficult in the off-road cases because if you're on-road, again, you generally know the environment you're trying to drive. You can generally specialize these algorithms for, let's say, a city, which is what you see a lot of times where you've got a dense map of your city, you know the weather and the areas you're trying to drive in, so it's more constrained. In the off-road case, we're entering areas where we have no prior data, and you might need to be deployed to an entirely new area the next day. So that makes the use of ML significantly more difficult because the ML is going to essentially overfit to your training data, right? And you cannot fully characterize every possible scenario you will ever see off-road. So there's a lot of edge cases that pop up in the off-road space. And the way that we primarily try to minimize that is through the use of that simulation stack. And so what we have done is stood up those simulation stacks to run 24/7. And then we try to look for areas of high variance. And so the idea being that we don't have the manpower to go out and collect every possible scenario, but what we can do is tell the simulator to automatically perturb things. And then when we see errors pop up in the autonomy, we can grab that data set and then look at it and say, okay, here's an edge case that we found, or maybe here's a set of edge cases and things like that. And you'll see similar things in the on-road space as well. It's just much higher dimensionality, at least in my opinion, in the off-road space.
Any further question? Almost 5 now. So thank you so much.
All right, thank you very much.
Speaker.
Thank you, everyone.